All right, so we will quickly review the problem that I gave as a class exercise last time, which is find machine precision. That basically, to a reasonable approximation, finds the precision epsilon, epsilon n, such that it has the following properties. For any number smaller than that epsilon, if I try to add that number to 1, computer will ignore it because it cannot handle the difference between 1 and that number. It's so small. And we know that those are the typical round-off errors that I have. I cannot find the exponent that will, together with this number, basically cover both and have enough details in Mantissa to actually include both of these results. Okay? So basically, one way to solve this is given here. Okay, so I decided to also count the number of iterations just because that it takes to do so. And I'm going to just start with a number, for instance, 1. And what I'm checking this result is 1 plus this epsilon. Okay, and I'm waiting for that number to be 1. Okay, so initially, if I just add 1 to 1, the result is 2 and obviously larger than 1. Okay, so I'm going to have a loop going while this number 1 plus epsilon is larger than 1. Keep doing. What am I supposed to do? I'm going to increase the iteration count just to count how many of these do I do. I'm going to record my previous value of epsilon. I'm going to just keep dividing this number by 2. The choice of 2 or 3 or 10 is up to you. The smaller the number here that is still larger than 1, the finer you will get and more iterations you will have. Okay. So either way, this will make my epsilon smaller and smaller with every iteration, and then I'm just going to update this 1 plus epsilon that I keep checking. If I don't update, I'm going to have an infinite loop because I'll never be able to get out of it. It's going to be whatever I set it to be at the very beginning. And when loops finishes, I can print this 1 plus epsilon, just in case. I can print what is 1 plus previous epsilon, just to see that previous iterations still had something larger than 0. And I might actually need to print quite a number. So this is a review of printing. So if I try to give 20 digits after decimal point, then I'll be able to capture actually the number. If I just print 5 or so, I might not see anything in this first 5 decimal points. So I'm just going to quickly execute this. So this is a script. It doesn't have input parameters. I can both run it from here and from just typing it in. So basically, this is what it executed. 1 plus epsilon is 1. That's why I got out of the loop. 1 plus previous epsilon, if I just print it, this is what I'm going to get, and I don't have enough details behind the decimal point to see that actually this number is larger than 1. Okay? So if I actually put previous... If I print it, I see it's about 2.2 times 10 to the minus 16. So that is the largest, the smallest number that I can add to 1 and still distinguish it as a separate number. Okay? Beyond that, I'm going to have round-off error. So this discussion sort of concludes our round-off errors, and there's one more error that we will look into. And this is something that before I actually get into it, I'm just going to review our measuring of errors. This is something that you already did in your homework, but essentially, when I'm looking at the error, I can either look at the absolute error, which is just the absolute value of the true value that I expect in my approximation that I computed, or the relative error. This is the most common one, because then when I'm looking at the relative error, I can actually see what is the method doing in different instances, right? So I can actually measure different, my ultimate result of a bridge, for instance, could be 100 centimeter in one case, 200 centimeters in another case, 500 centimeters in another, in the third case, and in all of those cases, I would like to compare them together, and I can compare them together only if I'm looking at the relative error. So most of the time, most often than not, you're actually going to look into the relative error, and that is your absolute error divided by the actual absolute size of the value you're trying to get. So for instance, if I'm measuring something that is 100 centimeters, and what I actually measure is 99 centimeters, it looks like a large difference. The difference is 1 centimeter, okay? But relatively speaking, it's 1 over 100, so it's only about 1%, okay? Whereas if I'm looking at something that is 1,000 centimeters, and my same absolute error is the same, it's 1 centimeter, relatively speaking, it's even smaller, and it's 10 to the minus 3, right? So it's 0.1%. And this is a much better method because I'm really looking at the relative error. Even though in absolute sense they're the same, relative sense, the second one is much more accurate. So that's why it's important to have to look at the relative error most of the time. Now, one thing that we haven't looked into is the truncation error, and it's also one of these unavoidable errors in computing. We cannot avoid it. We can just look at it and actually try to see how big it is. Okay? And that is the error that happens that anytime I have a formula that keeps going to infinity, okay, I will really, by necessity, only compute certain finite number of elements in this series. Okay? And I'm going to add them up. So no matter what, I'm going to chop off part of this formula. And I will look at the error that results, and I'm going to call it as truncation error. Okay? So then I will, when I try to store the result of this into the computer, I'm going to have round-off error on top of that. Okay? So those are two separate errors that we're looking into. Another common example in using approximate formulas is the one that we use for derivative. So for a very small class of functions like polynomials, trigonometric functions, and so forth, I actually have a formula that gives me what is the derivative of a function. For majority of data out there that we still treat as functions, for instance, Verilog data, it's simply data, it's points. Okay? So I don't have a sinusoidal or whatever combination of functions that actually describes that data. And for that, in such cases, I actually need to look at what's called a finite difference formula for approximating a differential. So for instance, if I'm looking at the derivative at a point, what I really approximate it as is the slope, okay, of a straight line close to the graph on that point. Okay? So basically I look at the 2 points, 1 point ahead of it, right? And I'm going to draw a tangent, and I'm going to look at the slope of that tangent. And as my difference between my xi when I'm measuring this and xi plus 1, which is the next point over, as the difference gets smaller, so does my error. Okay, so I get closer and closer to the actual tangent at this point. So this gets better, but it never gets precise. Okay, so it's never absolutely correct. So these are so-called finite differences. Okay? So Taylor series is one of the most commonly used. If you remember anything from calculus, it should probably be Taylor's formula, because it's used and abused over and over in engineering for all kinds of various applications. Now, whether you like it or not, that's a different question. Okay? But that's also one where it's one of the serious approximations, where if I want to evaluate the function near some function where I know the result, okay, then the value of function at x, which is in the neighborhood of x0 that I know, is f of x0 times the difference between these 2 points, or the distance between them, times the first order derivative of f evaluated at this point that I know, plus square of the difference divided by 2 factorial times the second order derivative of f, and I can keep going until I want or can't, okay? And whatever I chop off here is so-called on the order, so let's say that I stop at nth, okay, derivative, because that's as much as I wanted to compute, then the order of this remnant that I'm missing, that I'm chopping off, is n plus 1 polynomial in this difference between the point. So this is how small it gets. If this is a small number, this will be that much smaller because I keep multiplying with itself n plus 1 times, okay? And there's n plus 1 order of derivative of f here, okay? Which I'm hoping is relatively reasonably limited. It's not some huge number. So together, this term is relatively small, okay? But it's there, okay? So at some point, it might not even matter that I have zillion terms here, because round off error will actually dominate this one, right? So it doesn't really make sense to go forever in this formula, okay? So either way, this will get smaller and smaller, so I can stop. So one thing where we want to, so this is one of the examples that you will see commonly, and you will see it now in homework, where we will be able to, knowing the function, we will be able to evaluate what's the order of error, and there will be a number of examples like this, one coming up at the end of this class. Now, as we move on, so basically on Wednesday, we are starting the main part of the course, which will actually start with working some numerical methods that are actually solving something. So far, we've been building our toolbox in order to be able to do so. And one thing that you actually want to do is, when you derive a numerical method that does something, you want to figure out, well, when do I stop? When am I accurate enough? Okay? And do I actually, as I keep computing, am I getting closer to the solution that I'm looking for? Okay? So that is something that is called convergence. Convergence of an iterative scheme. I'm actually getting or converging to a true solution to a problem. There are cases with very ugly nonlinear problems. You will look into some of those when you get to transport phenomena. And there is a famous equation called Navier-Stokes equation, which in itself is a higher order partial differential equation that actually allows for multiple solutions, which is called bifurcation of the same problem in certain regimes, okay, certain flow regimes. So there are some ugly problems out there that actually allow for multiple solutions, and you sometimes wonder, well, okay, I designed a numerical method. Am I getting closer to something that makes sense? And if two things make sense, well, which am I getting closer to? Okay, and when do I stop? So there are definitely a lot behind the numerical methods. And the way we are actually looking into often to evaluate my error, okay, you notice that I said in the definition of error, my error is true value minus my approximation divided by the absolute value of true value, right? For that, I need to know what true value is. What if I don't? So if I need to know ahead of time what is the solution of my numerical method, well, why am I employing a numerical method if I know the solution, right? So often, you actually don't know. You're searching for a solution. You don't know it. So it's extremely hard, in most cases, to evaluate the error. Okay. You will evaluate the error in a couple of cases where you have an analytical solution, so you have something to compare to. But then when you move on to the problem that you don't know the solution for, okay, what you will actually monitor is whether your two iterations in two steps neighboring each other are getting close. So the implication is as I'm iterating and I'm coming with a solution like 1.001, then 1.0012, then 1.0013, right? And at some point, like all of these differences between the two steps will get smaller and smaller and smaller. So I'm thinking, I'm converging, I'm getting to a solution. Okay? So that's the only thing I can really monitor. So we will actually have this later in the examples. Okay? So when I don't know the solution, I'm going to be evaluating two steps of my iteration and see whether I'm getting smaller and smaller and smaller and smaller, and hopefully that whatever I'm getting, like this succession of numbers, is getting towards the solution to my problem. We will sometimes have a situation where I have multiple solutions and I'm getting closer only to one of them, because that's the best I can do at one time by running my numerical method. Okay? So just to review, errors in computing are unavoidable. Okay? Some of them are avoidable, and those are called bugs. But I treat them as unavoidable because humans are always going to have typos, and there are always things that you type in that you could have avoided typing in. Okay? You can find them and remove them, but they're always going to happen. So you have to work with that. Okay? Second part of these errors is those that you truly cannot remove. You just have to know what they are. Okay? Most often, it's not that bleak. Again, as I exemplified at the very beginning, if you're driving to San Antonio, all you need to know is how much gas in your tank you need to have. Plus, minus 1 pint, doesn't matter, right? So you just need a rough estimate to keep going. Right? And for most cases in applications, being within 1, 5, 10% of your solution will be just fine, because you otherwise can't even measure that you were not as close as you would perfectly want to be mathematically. So it's pretty good, okay, for most applications. Now the two errors that we have is one is round-off error, which comes from basically trying to fit a number, a real number with infinite number of digits into some finite memory in your computer. So you have basically round some things off. And truncation error, which basically if I have a mathematical expression that is very precise and infinite in its description, I will have to chop some part of that equation off and work with what I have. So they will typically you will often have problems that might have both of these. So this is basically the theoretical part, and now we will use the rest of this class to basically exercise. Okay? So here are the three problems that I'd like you to work on. Let's start with the first one, and then you and I will walk around and help. But first one is basically to just write down one piece of paper. And for number 2, what I mean by derivative, so what I'm actually going to copy, I'm going to copy this Taylor formula. Here's a Taylor formula. That might be helpful here.
So we can just evaluate it using one term. You said like 1, 2, 3, 4.
Your mind just went off. All right. So basically, no, this is for your. So x0 in this case is this 1, and you're trying to compute f of x, x being both 2 and 3, so 2 separate cases. And you will see that formula will not be equally accurate for both cases, and you will tell me what happens. And what I mean by using 1, 2, 3 terms, it's in this Taylor series. So this is 1 term, both of these are 2 terms, and then 3 terms. And supposedly, as you pile up more terms here that you're using, it's going to get more accurate. And since you know what f of x actually is, you can figure out how accurate you get.
Wait, that says from x to x, evaluate at x is equal to x not. That we for the second term, it's just
X, yes. So this is f prime of x. So you have to first find what f prime of x is, right? Oh no! That darn calculus class. Oh no! And I'm gonna also copy. This is the formula for derivative. Okay, that I mean. So this is finite difference. I'm gonna stop the movie because there will be a whole lot of silence in the movie.